So I didn't print. Okay. So a couple more things we need to talk about from chapter 55. You all have read all the way through chapter 55 now?
Yes, we have.
All right. All right. Okay. So we talked about food webs, and we had various stages in our food webs, and I just referred to them as stages, but from now on, now that we've got into ecosystem ecology, you're going to refer to these as trophic levels, right? Right?
Yes.
So we have trophic level 1. Trophic level 1. We've got trophic level 2. We've got trophic level 3. And sometimes we can have more. So let's go ahead and just give 4 trophic levels, okay?
What's the little 2 dots? Or the ones?
Same thing. So trophic level 2. Trophic level 3. Rather than just writing it. You've never seen this before? Oh, wow. That's so cool. When Michelle comes back. Yeah. All right.
Oh, yeah.
Okay, now, the first trophic level, these are primary producers. And why do we call them that? Why do we call them primary producers? Yeah, Emma.
They receive energy from the sun.
Right, so what are they producing? Organic material. They're not producing energy. Remember, first law of thermodynamics, you can't create or destroy energy, but they're producing organic material by harnessing sunlight. Trophic level 2, we call these primary consumers. Why do we call them primary consumers? Yeah, Katie.
Because they eat the primary.
Right, they're the first consumers. They're primary. They're the first consumers. These, what do you think we call trophic level 3? Secondary consumers. Love it.
And then tertiary.
And then tertiary. Secondary consumers. And then tertiary. Good. Tertiary, and then if we went up, it would be quaternary. And then I don't even know what it would be after that. Okay? So tertiary consumers. Yeah.
Could there be a secondary producer?
Not really, although there are some. So in order for it to be a secondary consumer, which as far, I've not ever seen that term applied, but you do have some primary producers that also eat organic material, like the Venus flytrap, or some corals that have photosynthetic dinoflagellates inside, but then also feed. And you might call some of those secondary producers, but not that I know of. Tori.
Is this like the energy pyramid?
We're getting there. This is going to shape our energy pyramid, but you're working ahead. But yes. Okay. No, you're fine. Okay, so when we look at ecosystems, remember we at the very end of 54 we talked about 2 different ideas of what shapes the community. We talked about bottom-up impacts or bottom-up effects, and we talked about top-down effects. Okay? When you get into ecosystem ecology, it almost always focuses on bottom-up effects. And so we refer to things like, from trophic level 1, we refer to like the gross primary production, the GPP, gross primary production.
And then the net.
Yep. So gross primary production is the total biomass of producers. Okay, so gross primary production is the total biomass of producers. It's basically how much of that sunlight is being converted into organic material. Okay? True or false? These producers use the sugar they make for their own purposes. So a plant, when it converts sunlight into chemical energy in the form of sugar, does it use some of that sugar for its own growth, its own development, its own reproduction, its own activities? True or false?
True.
Yes. So which means that not all of this primary production is available to the next level, right? So we have to minus a value, we call this RA, and this is the amount, I think it's assimilated respiration, but amount used in respiration. Okay, and respiration in science doesn't just mean breathing. You know, when we use respiration in medicine, like respirational therapy or respiration, you're talking about breathing, right? But respiration is the process of taking these sugars, these organic fuel molecules, breaking them down to release that chemical energy. Isabel.
What does GPP minus RA give you?
That's a wonderful question. Equals NPP, which is the net primary production. And so this would be the amount of material that is made by producers, the amount of organic material made by producers that's actually available for the rest of the community. Okay, is the net primary production. Yeah,
Can you
Trinity.
repeat what that is again? Sorry.
Yeah, so the net primary production, it's the total biomass of the producers minus the amount that those producers use for their own activities. So in other words, it's the amount of biomass available for the next trophic levels. So if you want to think about it this way, it's if you ate the plant, it's a percentage essentially of the sunlight that you get, right? Because ultimately this all goes back to sunlight, right? We talked last time that only a fraction of 1% of the amount of sunlight that hits the earth is converted into biomass.
Yeah.
Of that, a lot of it is used by the producers for their own activities, and only some of it is left and available for the next trophic level. Yeah, Isabel.
Biomass is what they can use to make energy, or?
Yeah, biomass is, so mass is the amount of matter in something, right? And then bio is living material, so it's the total amount of living material. So if you wanted to calculate the biomass in this room, we would just take the collective mass of all of us in this room, plus all the other living things in this room, some of which you can't see.
I didn't like that.
But that I mean, that would be minuscule compared to our,
Microbes.
yeah, microbes coating the surfaces, the counters, all over your tables,
The air.
backpacks, in the air. Okay? Does this make sense?
Well,
Well, this is cool, but this only tells us the next trophic level up. This only shows us up to trophic level number 2. But what if we wanted to represent the entire ecosystem, right? Not just how much of this is available to trophic level number 2, but how productive is the entire ecosystem? Okay? So what we're going to do is we're going to do a new value called NEP, which is net ecosystem production. And somebody explain this term for me. What does net mean? No, not all. That's gross. Trinity.
otherwise,
Emma.
you're sure.
Yeah, no, it's not average. It's what's left over after something is taken away. Right? Trinity.
What does that mean? Like, what does that mean? Like, when you say like net worth, it's just like.
Yeah, so net worth, it's how much all of their assets are worth minus all of their liabilities. So if somebody's worth $500 million, it means all of their assets combined minus all of their debt is equal to $500 million. And then so if you wanted to go gross worth, it would just be all of their assets together and would ignore their debt. So when you look up somebody's net worth, I don't know if you ever do this, but you're like, hey, The Rock, the highest paid actor last year. I wonder what his net worth is. And you look it up and it's ridiculous. It's like $400 or $500 million. Or Chris Pratt. Okay, so net ecosystem production. Now this is telling us how much of what the ecosystem makes in biomass is available to leave that ecosystem and go and feed other ecosystems. Right? This is good stuff. But how are we going to calculate this? How are we going to calculate the net ecosystem production? So it all starts with who is making the biomass? Who's making the biomass? Trophic level 1. And what is the total biomass that they make? GPP. So NEP is going to start with GPP, and we're going to now start taking it away, taking something away from it. And what's going to take away from this biomass? We already talked about what the plants are going to use, their respiration. Yeah.
The amount used by like the animal?
Yeah, and the amount that's used by trophic level 2, and the amount that's used by trophic level 3, and the amount that's used by trophic level 4. How much is available to leave that ecosystem? Or another way to think about it, to be reassimilated into the ecosystem by detritivores and decomposers as they break down these tertiary consumers and secondary consumers and primary consumers and even producers that die. And so now we're going to multiply or minus away. They call it something different. I think they do R sub E, but I'm going to do R sub total because I think that's a better way of thinking about it. And so GPP, we already know what that is, right? That's gross primary production, right? Which is the total amount of biomass of producers. And now we're going to subtract away our total, which is the total biomass used for respiration, which again is not breathing. It's actually taking those organic molecules, breaking them down, releasing the energy. Total biomass used for respiration in all, we'll just say species, all of our living forms. But this is awesome. Now we have a way to actually illustrate how productive is this ecosystem. We were just outside, right? Do y'all remember that?
Yes.
It was fun. I mean, it was fun for me.
I think we need to remind you when you go back to static.
Yeah,
Oh.
that's dramatic.
You know what? I mean, we can make an effort to go outside almost every day. We can't do it every class, but we can make an effort to do it almost every class. Okay, and I think that's probably a good effort to aspire to. Okay. So now, if we're like, okay, well, overall, this ecosystem is very dry and arid, right? Would you agree?
Yeah.
So overall, it doesn't seem like a great ecosystem for a crustacean. But there are what we call microcosms, small ecosystems within the bigger ecosystem. And we can measure the net ecosystem production of each one of those flower beds. We could do it. And it would actually be relatively simple. Okay.
How do you find the total biomass?
That's a good question. We'd either have to pull out all the producers and we would mass them, or we would find what that species is, figure out its average mass, figure out what its average size is, and we just do some calculations.
Oh, you weigh the...
Yeah, you can weigh the producers. That's what biomass is. I mean, it's not weight, it's mass, but if your gravity doesn't change, weight and mass are somewhat interchangeable. Right? Your mass is going to be the same here as it is on the moon.
Yeah.
But your weight's going to be different because gravity is lower on the moon than it is here. Okay? But since we're on Earth, mass and weight can somewhat be used interchangeably. Alright, does this make sense? So we can use this as a way to estimate the productivity of an ecosystem. Yeah, Michelle.
So just want to ask what's the difference between NEP and NPP?
NPP and NEP. NPP is focusing just on this trophic level. What's the net productivity of trophic level 1? NEP is focusing on the productivity of all trophic levels in an ecosystem. That makes sense? Okay. It's a good stuff, right? This is good stuff. Okay, I want to ask you a question, and I want us to come up with some thoughts together. Okay, may I erase this?
Yes.
Okay. Now, let's think about a fully aquatic ecosystem. Okay, give me an example of a fully aquatic ecosystem.
The ocean.
The ocean. So that's one big ecosystem. Let's just do a single part of the ocean, like maybe a coral reef.
Oh,
The Great Barrier.
The Great Barrier Reef, even that's massive. We'll just do like a section of coral reef.
Sector 1, 2, 3 of
Yeah.
Great
Okay, so what are keeping in mind that the two major aspects of an ecosystem is energy flow and nutrient cycling, right? Energy flow, nutrient cycling. Energy flows from sunlight ultimately to heat, which is useless. Nutrient cycle, right? We talked about that with carbon dioxide. So if you are a fully aquatic ecosystem, like a coral reef, what are the two most important things that are going to influence the amount of primary production? What are the two most important factors that are going to impact GPP? Isabel. Sunlight, because that's where the energy is coming from. And what else?
Oh, it's still on me?
Yeah, it's still on you.
Oh.
I mean, Emma can back clean up. Carbon dioxide. Okay, so a nutrient available. Okay, so sunlight and some kind of nutrient. Okay, what you'll find is carbon is incredibly important. We talked about that last time, right? Every organic molecule has carbon. The thing about carbon is there's plenty of it. There's a lot of it, especially in the oceans. Oceans do a really good job gathering carbon. We sometimes refer to them as carbon sinks because the oceans are really good at grabbing carbon and holding on to it. Okay, so what we find is that the most important nutrient in aquatic ecosystems is actually nitrogen. Nitrogen tends to be the nutrient that's going to determine how productive an aquatic ecosystem is. But anyways, we have energy in the form of sunlight, and we have nutrients. What about if you're a land ecosystem, a terrestrial ecosystem? What are the most important factors in determining GPP, the gross primary production?
Isn't it the same thing?
Same thing, sunlight and nutrients. And what you find in land, the most important nutrient is, again, nitrogen in terms of determining the productivity. Okay? Now, the neat thing about aquatic ecosystems is you get something that's called upwelling. Have you ever heard of that before? Okay, let me show you a water column. This isn't in the textbook. This is bonus information. You couldn't have read this, at least in this chapter. So you all should appreciate this. Be like, man, this is awesome. Man, this is awesome. Thank you. Okay, so here's a lake, right? It's a beautiful lake, okay? So here's a lake. One thing is that water the density of water varies with temperature, okay? The density of water varies with temperature.
What do you mean by that?
So when the temperature of water changes, the density changes.
So like if it's warmer, the density
It's lower.
Oh, that makes sense.
Yes.
Like about-
And so water reaches a maximum density at 4 degrees Celsius. That's where water reaches a maximum density.
32 degrees?
Celsius.
32 degrees Fahrenheit is freezing, 0 degrees Celsius is freezing.
40 degrees?
So 4 degrees would be, it's a little bit less than 40 degrees, about 38, 39 degrees, probably closer to 39 degrees Fahrenheit. But that's where water reaches its maximum density, because water's interesting. Usually the solid is denser than the liquid of a material. But you all know that ice is less dense than water, right? It floats on top. That's unusual. And so water reaches its maximum density at 4 degrees Celsius. And then as you move up the water column, the temperature increases, okay? Up to, probably 25 degrees Celsius would be, which is somewhere in the 70s, 78 maybe degrees Fahrenheit. And so what you'll find is in that water column, as you move up, the temperature increases because, water becomes less dense the warmer it is. And the less dense materials float on the more dense materials, right? Cool? All right. But what happens is when this water cools, if this becomes true, and we have 4 degrees Celsius all the way through, if it cools like in the wintertime, and you get 4 degrees Celsius all the way through, you can mix that water. And now the water that was down here can come up. Okay, so if this, then you actually get this water here coming up to the surface, and we call that upwelling.
Is that like good for the water?
Well, what do you think's down there? What's ice? Well, it's too warm for it to freeze. Because it freezes at 0 degrees Celsius. So it's too warm for it to freeze. But what happens when animals die in a lake? They sink to the bottom, right? Or at least some of the material ends up on the bottom. So what's down here?
Dead stuff.
Dead stuff. And what happens to dead stuff? Decomposers start eating them and unlocking the nutrients inside. So upwelling brings nutrients to the surface.
But aren't the producers, where are the producers?
The producers are up at the surface where the sunlight is.
That's why.
So they're making biomolecules, but they need nitrogen in order to do that.
Wait, the producers of a lake are at the bottom?
No, at the top. Yeah.
Okay.
Yep. I mean, you may have some grasses, that are in here and are producing,
Yeah.
but a lot of it are going to be algae that are up near the surface of the water. Okay? So when you get upwelling, it brings nutrients to the surface, and this equals an increase in GPP. Okay? So this happens in lakes all the time because a lake's small enough, as long as it's in a relatively cold place, you can get the water down to 4 degrees Celsius so you can get a nice thorough mix. Okay, notice it says if this happens, this is the norm. If this happens, then you can mix and you can release those nutrients and you can get an increase in GPP. But this is one thing that makes lakes particularly productive. Yeah, Emma.
Does the lakes have to be 4 degrees Celsius, or can they be like in different numbers all the same? It can be like 6 degrees Celsius throughout.
Oh sure, but that probably won't happen. This water down here is almost always going to be 4 degrees Celsius. Now you're thinking of like a small lake, like Pyramid Lake here, right? It's so warm here, I doubt the bottom's 4 degrees Celsius. I doubt it ever gets that cold. But in a pretty good sized lake, you're going to have cold waters down there, and it's going to get down to 4.
So
Yeah.
what about like an Arctic ecosystem? Like, how does that work? Like producers, are there producers in that?
Oh, absolutely. Yeah, so because when water gets really cold, you can mix it better. Arctic waters, like the Arctic Ocean, is way more productive than the tropical oceans. Way more productive. And that's why whales migrate north in the summertime and and are there in the fall because there's just an enormous amount of food there.
What are some of the producers?
Krill. Well, krill are zooplankton, but the producers are like diatoms, dinoflagellates, algae, these small unicellular photosynthetic organisms. And then the krill eat those, and the whales eat the krill. And other fish eat the krill, and then the whales may eat those fish. Yeah.
Like, can it ever get colder than that? Like 3 degrees or 2 degrees or whatever?
Yes. Yeah. Oh, absolutely. I mean, the top of a lake can freeze. I don't know if you knew that or not because you live in Southern California, but lakes freeze.
See it in movies.
Yeah, and so, but it's if the water is 3 degrees Celsius or 2 degrees Celsius, it's less dense than 4 degrees Celsius water, so it float on top of it. And that's why ice will form up at the
How
top.
is it less dense? Because like I can know that like 5 degrees would probably be less dense than 4 degrees.
Yeah, because once it gets under 4 degrees, it starts to crystallize. The water molecules start to stick more together, and because they can't freely make and break bonds anymore, they can't get as close together. Yep. Okay, so this makes, again, Arctic oceans way more productive than tropical oceans.
And what do you mean by mix the water? Like, how does that happen?
Well, the water, it just, when it's all the same density, it can mix, right? Because the reason it's separated is because one was more dense than the
Or
other.
what mixes it?
Itself.
Oh, okay.
Just its desire to make and break bonds with other molecules
Those
of water.
currents.
So we have an energy pyramid that we can construct. And here's trophic level 1. Here's trophic 2. Here's trophic 3. and here's trophic 4. And we can estimate the amount of energy or the amount of biomass you should find at each of these levels. Because only about, let's say this is 1,000 kilograms of mass. And I know in the book, if you looked at this pyramid, which you should have, they did it in joules rather than in mass, but I'm going to do it in mass. They did it in energy, but I'm going to do it in mass. Okay? So if we had 1,000 kilograms of biomass here, you should only be able to have about 10% of it here.
Okay, so you lose 90%.
Yeah, 90% of the mass formed here is not available here. Either it's undigestible material, or, you know, the plant's not all of it is eaten, or some of it just doesn't get eaten, period, and then a lot of it is used by the plant's own materials. And then so here, you would be able to have 10 kilograms of biomass, and here, you would be able to have 1 kilogram of biomass, which is about 2 pounds. And you're like, what kind of apex predator is only 2 pounds, and why do we only have 1 of them? Well, this is an obnoxiously small amount of biomass. But this right here is 2,000 pounds. So it just gives you an idea of how much biomass there actually is of primary producers, right? There's going to be a lot. Yeah, Isabel.
So that's energy transferring up?
Well, it's in this case it's biomass. Kilograms is a measure of mass, but you could do the same thing for energy.
So when that's energy, by trophic level,
Yeah.
okay, so that 90% that's not being, that's not passing down, is that because the person, the thing that's using it is using that 90%?
Yes, it's using some of that for its own life processes, and then some of it's being lost as heat that's unusable. Yes, absolutely. Okay, yeah, Mark.
One other thing that's really interesting is how like basically the predator for one thing can also can also be the prey for another bigger.
Yep.
Like the like smaller sharks.
Absolutely.
And like compared to like maybe like if like an orcas around.
Sure. So let's think if this trophic level 4 is a 30-ton blue whale.
Ooh.
A 30-ton blue whale that feeds on organisms here, the krill, that feed on the producers. And so how much krill does it take to feed a 30-ton blue whale? A lot. And how much krill does that amount, or how many producers does that amount of krill have to eat in order to assimilate that biomass and be available to be eaten by blue whales? A lot. So it just shows you how productive some of these waters can be. All right? Have a wonderful day. I will get you all a study guide out either today or tomorrow.
Oh my gosh,